She also
I know
you
it's-
saw it in black and white.
I know it's not that, but it's like hard to believe.
It shouldn't be that hard to believe. All right. So again, this will not be on next week's quiz, which is on Monday, nor will it be on next week's test, which is on Thursday. So segment relationships in circles. So we've been dealing with arc measures and angle measures and stuff like that. Here we're going to be dealing with the lengths of segments. So this first theorem, if two chords intersect in the interior of a circle, then the products of the lengths of the segments of the chords are equal. That is a lot of prepositional phrases strung together. No, it's not a run-on sentence.
Miss Freeman would say otherwise.
No, she wouldn't. She knows what a run-on sentence is.
I don't.
Don't use of. It's a no-no word.
Of is a no-no word?
Yes.
We had like a list of words we can use.
I don't think it was.
I thought we couldn't use it unless it was necessary.
No, that. That's what was that.
Just hate me.
Okay.
That's parallel structure.
You would never be able to lesson in that.
No, it's not.
I say I don't think this is parallel structure either. Anyway, so what that means in this diagram, the two parts of chord JM multiplied together will be equal to the two parts of arc AS multiplied together. It's a pretty simple theorem once you break it down that way. You're like, oh, the two parts of this chord multiplied together are equal to the two parts of this chord multiplied together. Now, another important question would be, well, why is that true? Okay, so let me just real quickly, you don't need to write any of this down, but please follow along with me. Let me show you why. If I was to fill in segment SE and segment JM, or JA rather, notice that arc angle J, intercepts this big arc from A to E down here, and so does angle S. So what does that mean about those two angles?
Equal.
Yeah, they're congruent to each other. Likewise, this angle at A intercepts arc JS, and the angle at E intercepts arc JS. So those two are congruent. So what does that mean about these two triangles?
Similar.
They're similar to one another by angle-angle similarity. And since triangle JAM,
Do we write this part down?
no, you don't need to write any of this, is similar to triangle SEM,
Smeet. Oh.
Are they similar by angle?
right? They're similar by angle-angle similarity. So that means that JA is to SE as AM is to EM as JM is to SM. Right? When triangles are similar, the corresponding sides are proportional. Yes, ma'am.
Why do you only need two angles to
That's all it takes. Angle-angle similarity, baby. You gotta know those.
The third one. Then why do you need to prove they're congruent? Why do you need three?
Because that's the difference between similarity and congruence. That, and if two angles of this triangle are congruent to two angles of that triangle, the third pair of angles are automatically congruent.
Third
Third
angle.
The third angle theorem. So if you have two, you automatically have three.
I missed
There's a
those
180.
days. That was so
That was so
useful.
nice.
Okay.
Beautiful proofs.
So focusing just on this part, if you were to cross multiply, you'd have JM times ME is equal to AM times MS. So it all works. It's a lot easier just to think of it this way than it is to go back and do all the similar triangles. Okay, so let's do an example problem. Can you wait till the end of the lesson? Thank you. So here we want to find the value of x and the length of each chord. Okay. So here I know that the two parts of chord YA multiplied together, 14 times x, is going to be equal to the two parts of the other chord multiplied together, 7 times 10. So 14x is 70. We get that the length of x is 5. And then they want us to find the length of each chord. So YA is just 14 plus the 5 is 19. And KR is 7 plus 10 is 17.
This is easy.
Yes.
I said that before I got this.
Okay, so for chords that intersect in the interior of a circle, that's all there is to it. All right. Well, what if we have things that intersect in the exterior of the circle? So if you have two secants that have a common exterior point, then the product of the secant segment and the external secant segments are equal. The secant segment is from F all the way to I, or from H all the way to I. The external secant segment is the part of the secant that is outside the circle, from A to I and from T to I. Again, you could show this by similar triangles. I'm not going to take the time to do it, having done it already once. It's a little uglier on this one, but it's, again, pretty easy. The whole thing times the outside piece is equal to the whole thing times the outside piece. So, let's take a look at this one. So we want the whole thing times the outside piece. Oh, this whole secant segment is x plus 8 multiplied times the outside part is 8 is equal to this whole secant segment is 9 plus 7 is 16 times the external part, 7. So this will be 8x plus 64 is equal to 112. So 8x is 48. Means that x is 6. Then it wants the length of each secant segment, so that's dt, which will be 6 plus 8 is 14. And LT, which we already found, was 9 plus 7 is 16. And I think the reason your book is big on having you find the lengths of the whole secant segment or the length of the whole chord is to remember those aren't going to be equal to each other. All right. Last one. If you have a secant and a tangent, and they have a common exterior point, we still do the secant part the same way. The whole secant segment multiplied by the external part is equal to the tangent segment squared. Now, think about why that makes sense. Here we did the whole thing times the external part. Aren't we doing the whole thing times the external part here also?
Oh, it's the whole thing and the
Are the same, yeah. So it's really not any different than the last one. So here, we'll do the entire secant segment, 20, times the external part, 5, is equal to x squared. So x squared is equal to 100. So x could be positive 10 or negative 10, but this is the length of a segment, so it can't be negative 10. So we throw that out. That's something that, I mean, right, in Algebra 2 that comes up a lot, where you've got to look at the positive root and the negative root. You can't just look at one. In geometry, we tend to ignore the negative root a lot of times because it's the length of a segment or the measure of an angle, and that's just not possible for them to be negative. Okay? All right, any questions? Okay, then your homework is once again in the book.